Limits at infinity and horizontal asymptotes. Alright, so now let's take a look at the definition of a limit at infinity. If, as x moves increasingly far from the origin in the positive direction, so if x is headed towards infinity, if the function values f of x get arbitrarily close to some number L, then we write the limit as x approaches infinity of f of x equals L. And we call this a limit at infinity. And similarly, if the x values are moving increasingly far from the origin in the negative direction, so if x values are headed towards a negative infinity, if the function then gets arbitrarily close to some number L, then we write the limit as x approaches negative infinity of f of x equals L. So let's take a minute to distinguish between a limit at infinity and an infinite limit. So a limit at infinity is either one of the following. So the limit as x approaches infinity of f of x has to equal some real number L, or the limit as x approaches negative infinity of f of x has to equal L. So a limit at infinity means that the x values are getting really, really big in the positive direction or in the negative direction. And then the f of x values, the function values, get close to some real number L. As opposed to an infinite limit. So an infinite limit said, well, I want to get close to some number, not infinity, of the function. And when I get close to some number, what's going to happen is my y values go to either positive or negative infinity. So an infinite limit has infinity as the solution, as the answer. But remember, these limits do not exist. So here in this limit at infinity, we're going to get out a real number answer. So our limits at infinity, if we get out a real number answer, are going to exist. So the infinity is in a different position, basically. A limit at infinity, the infinity we're concerned with is in regards to the x value. An infinite limit, the infinity is now the y value. So let's look at an example. We're going to consider the function 1 over x, the reciprocal function, and we're going to take a numerical approach first by creating a table. So we're going to take a look at what happens when we let x values get really big in the positive direction and really big in the negative direction. So this left side, I'm going to start by letting x equal 1, and then I'm going to keep going up. So I'm going to let x be 10, and then 100, and then 1,000, and then 10,000, and then I'm going to let x be 1,000,000. And then I want to figure out, well, what's happening to the function 1 over x. So if I substitute in 1, 1 divided by 1 is just 1. If I substitute in 10 for this x, then I get 1 over 10, which as a decimal is 1/10. And if I substitute in 100, I'm going to get 1 over 100, which as a decimal is 1/100th. And I can continue this. So this is 1,000th, right? 1 over 1,000. I'm running out of space here, but you can see what's happening to the function values is that they're getting really small. So 0.01, 0.001, 0.0001, and then here, so now we have 5 zeros past the decimal and then a 1. So this is getting closer and closer to 0. So as my x values get bigger and they're positive, so as x approaches infinity, my function values are getting smaller and smaller and smaller. So f of x is approaching 0. Now, will it ever equal 0? No, it will not ever equal 0, but let's remember what a limit is. A limit only cares about how arbitrarily close I can get to some number, not that I ever actually reach it. So here, what we would say is that the limit as x approaches infinity of 1 over x equals 0. And now let's see what happens as I plug in negative values that are getting more and more negative. So if I plug in -1, -10, -100, all that's going to happen is that I get out -1, -1/10, -100th, -1,000th. So even though they're negative, these numbers are still getting closer and closer to 0. So negative 0.000001 is still getting closer to 0 just from the negative side. So as x values get really big in the negative direction, my function values are still going towards 0. So the limit as x approaches negative infinity of 1 over x is also 0. So now 1 over x is a basic function, so we should know its graph. So let's take the graphical approach next. So here we have the graph of 1 over x. It is one of the basic functions, so we should know that it has a vertical asymptote at x equals 0 and a horizontal asymptote of y equals 0. So if we look at this graph, if we were asked to analyze the limit as x approaches infinity, so here's the x-axis, the horizontal axis. So where is infinity? Positive infinity is way over here. So what we're looking at, what we want to do is we want to trace the function, and we want to say, well, where is the function headed as I move towards positive infinity? So look, it's getting closer and closer and closer and closer to a y value of 0. So remember, limits are all about the y value. What y value am I getting closer to? So as x heads this way, my y values are getting closer and closer to 0. So that matches our numerical approach that the limit as x approaches infinity of 1 over x is 0. And now as I approach negative infinity, so as I head this direction towards negative infinity on the x-axis, let's trace the function and see, well, what y values am I getting closer to? So the y value I'm getting closer to again is 0, this time from negative values, but I'm still getting closer and closer to 0, which again matches my numerical evidence. So notice I've been using this word approaching here, and I did say that we should know that there's a horizontal asymptote here at y equals 0. So let's recall what an asymptote is again. An asymptote is a line that we approach towards the ends of the function. Well, the ends of the function are when we head towards positive infinity and negative infinity. So we should think, or we should sort of make a connection here, that when we're considering limits at infinity, we're considering what happens at the ends of the function, and we're really thinking about is horizontal asymptotes. So let's just quickly notice that the horizontal asymptote was y equals 0, and what did each of these limits end up being? They ended up giving us a result of 0. So just keep that in mind as we move forward. Now let's take a look at a theorem. The theorem says that if r is a positive rational number and c is any real number, then the limit as x approaches positive or negative infinity of c divided by x to the r equals 0. So here's an easier way to think about this theorem. The theorem says that if the denominator of a fraction gets bigger faster than the numerator, and in this case the numerator is constant, so it's not even going anywhere, then the entire fraction goes to 0. So let's think about this with a quick example. So let's go ahead and say I want the limit as x approaches infinity of, let's go ahead and put any old number, so we'll put 8 over x to the r. So r is a positive rational number. So let's say x cubed. So the limit as x goes to infinity of 8 over x cubed. So remember what we did when we created a table of values, right? So we just went ahead and started plugging in big X values. So we started with 1, and then 10, and then 100, and we just can keep on going. And we want to know what happens to the function. So in this case, what happens to 8 over x cubed? So when I substitute in 1, 1 cubed is 1, 8 divided by 1 is 8. So let's see what happens when I plug in 10. So what I'm going to get is I'm going to get 8 divided by 10 cubed. So I have 8 divided by 10 cubed is 1,000. So 8 divided by 1,000 is 0.008. It's 8 thousandths. So notice what just happened. I went from 8 to 8 thousandths. So this number is getting smaller already. So I can imagine that these numbers are going to get closer and closer and closer to 0 as my theorem tells me. So what's happening is the denominator is growing, right? So if I go ahead and substitute in big values in for x, and then I cube those values, they're going to get even bigger. So if the bottom of a fraction is really big, and the top is constant, so it's just the number 8, it's unchanging, if the bottom gets bigger faster than the top, then the whole thing is always going to go to 0. And it didn't matter whether or not x was approaching positive infinity or negative infinity. All that's going to happen is now I'm going to get the values -8 and -0.008, and that's not really going to affect anything for me. It just means I'm getting closer to 0 from beneath the x-axis. So I'm approaching 0 from negative values, but still approaching 0. So now we're going to look at the connection between limits at infinity and horizontal asymptotes. So earlier I asked you to keep in mind during the example of the reciprocal function 1 over x that when we considered the limit toward both infinities, positive and negative infinity, we got out an answer of 0. And it also just so happened that the horizontal asymptote in that problem was y equals 0, and that's not a coincidence. So the formal definition of a horizontal asymptote is a line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b. So here's an important thing to keep in mind, that if a question asks you to find all horizontal asymptotes of f of x, that's equivalent to asking you to find two limits, the limit as x approaches positive infinity and the limit as x approaches negative infinity. So let's just take a look at two quick examples. I'm going to go ahead and draw two different xy planes and two different functions. So let's say I have the reciprocal function that we took a look at earlier, 1 over x. So 1 over x looks like this, and it has a horizontal asymptote at y equals 0. And if we wanted to find the horizontal asymptotes, what we'd have to do is both limits, the limit as x approaches positive infinity of 1 over x and as x approaches negative infinity of 1 over x. But what we'd get in this problem is we'd get 0 both times, because there is in fact only one horizontal asymptote. But there are other functions that have more than one horizontal asymptote. So for example, the arctangent problem. So the arctangent function, looks like this, and it is one of the basic functions as well, and it has horizontal asymptotes at y equals pi over 2 and y equals negative pi over 2. So you'd notice that if we took the limit as x approaches infinity of the arctan function, that you'd get out positive pi over 2. So as you're approaching positive infinity, let's try in a different color. As you approach positive infinity, what's happening to the function? It's getting closer and closer and closer to pi over 2. So the limit as x approaches infinity of arctan is pi over 2. And we can do the other limit as we approach negative infinity of the arctan or tan inverse function, and we get closer and closer this time to negative pi over 2. So when we get out two different answers, it means we have two different horizontal asymptotes. So it's important to know that when a question asks you to find all horizontal asymptotes, then it really means find the limit as x approaches positive and negative infinity. And formally, a horizontal asymptote is when a limit at infinity equals a particular real number value. So remember again, we can't have the answer be positive or negative infinity. Then the limit doesn't exist, and that is not considered a horizontal asymptote. So you can't say infinity is any type of asymptote in a problem. Alright, so the connection that horizontal asymptotes are really limits at infinity is going to help us solve certain limits at infinity of rational functions, because there's a nice set of rules to help us find horizontal asymptotes of a rational function. Now, this is the rule. If f of x is some polynomial over another polynomial, where the polynomial in the numerator, the degree is m, and in the denominator, the degree is n, and the coefficient of the numerator, the leading coefficient is a, and the leading coefficient of the denominator is b. To find horizontal asymptotes, all we need to do is compare the degree of the numerator and the degree of the denominator. We compare m to n. So there's three possibilities. Well, m could be less than n. The degree in the top could be smaller than the degree of the bottom. Now, if that happens, the horizontal asymptote is 0. The second case is if m equals n. They have the exact same degree in the numerator and in the denominator. And in that case, the horizontal asymptote is y equals a over b, the leading coefficient in the numerator over the leading coefficient in the denominator. And in case 3, if m is greater than n, there is no horizontal asymptote. So we're going to take these rules and we're going to tweak them a little bit when we think about them to help us solve limits at infinity. So let's go ahead and do a couple of examples now. Alright, now let's go ahead and try and solve these limits at infinity while keeping in mind the rules for finding horizontal asymptotes. So the limit as x approaches infinity of 2x to the fourth minus 5x plus 1 over negative 5x to the fourth minus 8. So if we relate in our mind the notion of limits at infinity and horizontal asymptotes of rational functions, what I can think about is that the highest power in the numerator is 4 and the highest power in the denominator is 4. So my rules for asymptotes tell me that this function would have a horizontal asymptote at 2 over negative 5, or negative 2/5. So this function would have a horizontal asymptote at y equals negative 2 over 5. So that is actually going to be the solution to this limit at infinity, is negative 2 over 5. Now you should hopefully remember this problem. This is the one that we did the long way. So notice it was a lot quicker when we thought about limits at infinity using rules for horizontal asymptotes. So let's do another example. We have the limit as x approaches infinity of x squared minus 1 over 3x cubed plus x minus 1. So again, we're comparing the highest power in the numerator and the highest power in the denominator. So when the denominator is bigger than the numerator, then the horizontal asymptote is y equals 0. So that's going to be the case here. The limit at infinity here is going to be 0. But at this point, I want to take the time to stop and think about something for a second. Remember that limits at infinity, what we're doing is we're plugging in bigger and bigger values in for x. So the reason why this goes to 0 is because if we think about plugging in a really big number into every x here, well, there's something called the dominating term. And the dominating term is actually what we consider when we look at the highest power in the numerator and the highest power in the denominator. So in the numerator, what dominates all the rest is x squared. So as I start to plug in really big numbers, this minus 1 is kind of negligible. We can almost kind of ignore it, right? When I start talking about plugging in a million, minus 1 doesn't really matter that much. So x squared is sort of what matters in the numerator. And then the denominator, well, 3x cubed is the term that matters because it has the highest exponent. So again, as we start to plug in numbers like a million, plus x, or plus a million minus 1, isn't really the important part here. It's not the part that's dominating. The part that's dominating is 3x cubed. So this function is really like considering the limit as x approaches infinity of just the dominating term in the numerator over the dominating term in the denominator. So it's like looking at x squared over 3x cubed. And we can simplify this. This would simplify to, well, the x squared would cancel and give me a 1 in the numerator, and x cubed would cancel and just give me an x. So I'd get 1 over 3x. So here, if I plug in infinity now, I can see that this is going to go to 0. So it's like the rule that we discussed earlier, where if the denominator is growing bigger faster, so here the dominating powers on the bottom, 3x cubed is bigger than x squared, the bottom grows bigger faster in a fraction, the whole thing goes to 0. So this ends up being 0. Now, here's the tricky part of me showing you this, is that I don't want you to ever write this out as equals. So this limit does not equal this limit. This is more what you want to think about, or this is like scratch work, is considering the dominant term in the numerator and the denominator. It's what you think about, right? You think horizontal asymptotes, but you don't actually write that this previous limit equals this limit. That's not true. It's just what you think about. And we're going to need this thought process when we look at the next problem. So the limit as x approaches infinity of x to the fourth plus x over x squared minus 3. So let's go ahead and circle the highest power in the numerator and the highest power in the denominator. So we have this x to the fourth on the top and this x squared on the bottom. So if we again think about dominating terms, x to the fourth is like winning the race. So if I think about plugging in really big numbers and taking them to the fourth power, that's going to grow faster than taking a number and squaring it. And so these other parts are kind of irrelevant, right? They kind of don't necessarily matter. Again, I don't want you to cross these parts out when you're doing your work. This is just what you're thinking about. So you're kind of just looking at, I'll highlight it, x to the fourth and x squared. Now my rules for horizontal asymptotes don't really help me here, because all the rules for horizontal asymptotes do is tell me that there aren't any. There are no horizontal asymptotes, but there is an answer to this limit. So here, if I plug in really big numbers, again, like 1,000,000, and take it to the fourth power, and then I take 1,000,000 and square it, well, who's winning the race is the numerator. So the numerator is getting really big, faster than the denominator. So this whole thing is going to go to infinity. It's going to go to positive infinity. So if I have bigger numbers on top than on the bottom, I go to either positive or negative infinity. Well, here, this was positive x to the fourth and positive x squared, and I was going towards positive infinity. So my answer is positive infinity. Now, this rule helps, but you still have to do some thinking about it when you have negative infinity or when you have other signs as leading coefficients other than positive. So let's take a look at the next example. I have the limit as x approaches negative infinity of negative 2x squared over 3x plus 1. So this is the first one we have where the limit is approaching negative infinity. And if we take a look at the powers, the power on the top is 2, the power on the bottom is 1, so 2 is bigger than 1. All we know is that there's no horizontal asymptote. So our answer is going to be either positive or negative infinity. But which one? So here's where we think about that dominating term thing. And here's what you can write. That this acts like. So it's not equal to, and I don't want you to write equal. But this limit acts like the limit as x approaches negative infinity of the dominating term in the numerator, so negative 2x squared, over the dominating term in the denominator, 3x. And then we simplify this. So the limit as x approaches negative infinity, the x in the denominator would cancel with 1 on the top, and what we'd get is negative 2/3 x. So let's think about negative 2/3 x. That's a line with a negative slope. So negative 2/3 x looks something like this. So what happens when I think about where the y values are going when I plug in negative x values? So as I head in the direction of negative infinity, where do my y values go? They go up to positive infinity. So here, the answer is positive infinity. So there was quite a bit of thinking about to do, even though we compared the power of the numerator and the denominator. That was a great shortcut for the first and second problem. But when it came to the third and fourth problem, we had to think about it a little bit more, especially this fourth problem, in thinking about the dominating terms and what happens when I plug in now really big negative numbers. So if I plug in a negative number right here is another way to think about it, like negative 1,000,000 times negative 2/3, a negative times a negative is a positive. So that's why I head towards positive infinity. Or looking at the graph is another perfectly good way of determining which infinity we head towards. Alright, let's do a few more examples. So the limit as x approaches negative infinity of 1 minus x squared over 3x squared plus x. So again, our rules for horizontal asymptotes, the highest power in the numerator is x squared. So a lot of people are always going to want to go to the first term they see, but we're looking for the highest power of x, the highest exponent is the degree. So x squared on the top, x squared on the bottom. So when they match, we analyze their leading coefficient. And again, the leading coefficient is the number in front of the highest power of x. So there's a negative 1 in front of x squared, and there's a 3 in front of x squared. So this limit is going to be -1 over 3. So that's it for the first one. It's pretty straightforward application of our rules for horizontal asymptotes as our little shortcut. In this next example, the limit as x approaches infinity of 2 divided by x to the 7th plus 5. So again, we're comparing our x's, or the degree of the numerator and the degree of the denominator. Well, in the numerator, we have an x to the 0 happening here, because anything to the 0 is 1. So clearly, the denominator is what's growing faster because it actually has an x in it raised to some positive whole number value, x to the 7th. So when I think about plugging in really big numbers, and I compare the numerator and the denominator, who's winning the race? The denominator, right? The denominator is growing really fast, so I'm plugging in a number and taking it to the 7th power, and then adding 5, right? So the denominator is really big, the numerator is just 2, it's a constant, so this is going to go to 0. And our rules for horizontal asymptotes follow that same solution, matching what we just discussed, because the power in the numerator is smaller than the power, or the degree, in the denominator, and that is when the horizontal asymptote is y equals 0. And the last one I want to talk about is kind of tricky. We have this square root in the problem. So we have a limit as x approaches infinity of the square root of x squared plus 5, and the denominator is x plus 1. So what you might be thinking is that in the numerator, the highest power of x is 2. And that would be incorrect. And the reason is because of this property. When I have the square root of just x squared, the square root of x squared turns out is plus or minus x, right? The square root of a square, they cancel, and I'm going to end up getting plus or minus x out as the solution to this problem. Now, I'm going to have to take that back over to this limit and give it some thought. So again, if I plug in really big positive numbers into x, like 1,000,000 here for x, and square it, plus 5, again, sort of becomes irrelevant. So the plus 5 is kind of something I can cross out in my mind, not necessarily on the paper like this. And if that's the case, then this limit acts like the limit as x approaches infinity of the square root of x squared over x plus 1. Well, we just agreed that the square root of x squared is plus or minus x. So this is like the limit as x goes to infinity of plus or minus x over x plus 1. But we can't have plus or minus x be an option. We have to make a decision. So how do we decide? Because the limit as x approaches positive infinity means that the only values we're plugging into this x are positive values. So the decision between plus or minus is that we're going to go ahead and choose, we're going to go ahead and choose just plus. So we're just going to have positive x in the numerator because the only values we're substituting in are positive x values. So now this limit at infinity is x over x plus 1, and the degree of the numerator and the denominator are the same. So the rule for horizontal asymptotes says take their leading coefficients. So the answer here is 1. And we take that back to the original problem and say that this limit at infinity is actually 1. So a lot of students are going to see x squared and say that the power in the numerator grows faster, but we can't forget to take into account the square root and then apply this property, and then we have to determine if we're taking the limit towards positive or negative infinity to decide which x value we use to solve this problem. Alright, so now we're going to look at one last example just to cover all the different types of problems you could see. So here we have the limit as x approaches infinity of the cube root of x squared plus 1 over x squared minus 4. So now we have a cube root instead of a square root, so let's see how we would handle this. So in the denominator, the highest power of x is x squared. So let's go ahead and pull a problem to the side that this sort of acts like. So this acts like, in the denominator, like x squared. Now in the numerator, this plus 1 again is going to end up being sort of irrelevant as I start to plug in really big x values. So the numerator acts like the cube root of x squared. So now let's go ahead and think about this. I have the limit as x approaches infinity. The cube root of x squared can be written as x to the 2/3. So if you need review on that, how to transform that, the cube root of x squared, into x to the 2/3, then come and see me and we'll review it, but that's definitely a property of radicals that you should know. And in the denominator, I have x squared. So, since the power in the denominator is bigger than the power in the numerator, so 2 is bigger than 2/3, then we know that the limit is going to go to 0 because the horizontal asymptote of this function is 0. So that means the original limit we were trying to solve equals 0. The next thing we're going to do is we're going to analyze which function or class of functions grows faster as I head towards infinity. So this is a little inequality tree that determines which functions are bigger than other functions as we head towards infinity. So the smallest growing function is logarithms. So here I have drawn the natural log function, and as we head towards positive infinity on this function, we can see that this logarithm, it's heading towards infinity. So it's going to keep going and going and going up, but it's growing pretty slowly. As opposed to polynomials, the next class of functions that's going to grow a little bit faster. So here I've went ahead and drawn x squared, and as I head towards positive infinity, I'm heading towards positive infinity in the y values, but I'm growing much faster than the natural log function grew. But polynomials are still smaller than exponentials. So here is the graph of e to the x, so here is infinity over here. And as I start to look at values closer and closer to infinity on the x-axis, my y values are definitely going towards infinity. So all of these are heading towards infinity. But exponential functions grow even faster than polynomials. So these values are going to rapidly start getting bigger and bigger as I move along the x-axis. But what grows even faster than exponentials is factorials. So factorial is the notation, right, with the exponent. So if you remember the rules for factorials, just a quick reminder, 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And these, in fact, grow faster than exponential functions. So you can see that 3 times 2 times 1 is 6, and then 4 times 3 times 2 times 1 is already 24. So it's a huge jump. Just going from 3 to 4, we go from 6 to 24. And then if we even compute 5 factorial, that's 120. So another huge jump just by going up an integer value. So the factorial function actually grows faster than any of these other functions. So which functions grow faster toward infinity? Here's the order. Logarithms grow the slowest, then polynomials, then exponentials, then factorials. And we're going to use this information to help us solve limits at infinity. Alright, so now we have the limit as x approaches infinity of x cubed plus x plus 1 over e to the x plus 1. So here, the rules for horizontal asymptotes don't apply. Not that these limits don't represent horizontal asymptotes, they do, it's just that there's not a polynomial in the numerator and one in the denominator. We have this exponential. But that whole concept of who wins the race is going to help us solve this limit at infinity. So in other words, if the bottom grows faster than the top, then the whole thing goes to 0. So we said exponentials grow faster. So if the bottom is getting bigger faster than the top, right, this one grows slower than an exponential. So if the bottom of a fraction gets big and the top grows slower, then this whole thing is going to go to 0. So there's really no work involved in these problems. It's a matter of knowing which functions are bigger towards the ends, right, towards the infinities, to determine whether or not this ratio ends up going to 0. So let's take a look at another one. We have the limit as x approaches infinity of e to the x over natural log of x. So we concluded that exponentials grow faster than logarithms. This one grows pretty slow. So if I plug in big values for e to the x, so if I plug in infinity here, this is going to get really big and this is going to grow slower. So if the top is growing bigger faster and we're going towards positive infinity, then this whole answer is going to go towards positive infinity. Alright, so now we're going to do the last two examples of limits at infinity, where we're going to analyze the limit as we go towards positive and negative infinity of just e to the x. So we've mostly been analyzing rational functions, but now we're just going to go ahead and look at e to the x and think about what happens as I start to substitute in values for x that are getting really big into this exponent. So remember, e is just a number. So as I start to increase the exponent, e to the x is just going to get bigger and bigger and bigger. So it's going to go towards positive infinity. So the limit as x approaches infinity of e to the x is positive infinity. So what about the limit as x approaches negative infinity of e to the x? Is it going to be negative infinity? So let's think about it for a second. Here, we thought about maybe plugging in e to the 100, and then e to the 1000, and then e to the 1 million. And these are getting bigger and bigger and bigger, so these are headed toward infinity. But what happens when I plug in big negative numbers in for x? Like, what about e to the negative 100? Well, when I have a negative exponent, it moves the entire term to the bottom of the fraction bar. So e to the negative 100 is 1 over e to the 100. So if we think about this as a number, is this a big number or a small number? Well, the bottom of the fraction is big, and the top is a constant. So this is actually a small number. So what happens if I continue to plug in bigger negative values? So e to the negative 1000 or more negative. So e to the negative 1000 is 1 over e to the 1000. So e to the 1000 is an even bigger denominator than e to the 100. So this number as a whole is smaller than this number. So what's happening is that these are getting smaller, and in fact, they're getting closer and closer to 0. So remember, when the bottom grows bigger faster, then the whole term goes to 0. So this limit is actually 0. And now let's just take a quick look at the graph of e to the x and see if what we just did makes sense. So the graph of e to the x, as we should know, has a horizontal asymptote at 0. And then it continues going up and up and up if we move off to the right. So as I approach positive infinite values way over here, where does my function go? My function goes towards y values of positive infinity. But as I head towards negative infinity, then my values are getting closer and closer to 0. So knowing the graph of e to the x definitely would have helped this problem if we just would have drawn it from the very beginning, but it's important to understand what happens and the notion of plugging in numbers to think about where a function is headed, and that really is like the crux of what a limit is. Where is a function headed? What's it getting closer and closer and closer to? A particular number like 0 or an infinity, positive or negative. So this limit actually doesn't represent a horizontal asymptote, but this limit does, because we have a horizontal asymptote on the e to the x function at y equals 0.